Hello everyone, I am Deeksha and today I'll be presenting my work on novel Bayesian framework to train deep networks with noisy labels in dataset with focus on epileptic seizure detection. EEG is a high-dimensional temporal signal collected from multiple positions on the brain scalp. EEG is typically the first modality used to monitor epileptic patients with recordings lasting several hours. Following this, trained experts manually go through such long recordings to localize seizure and create epileptic seizure datasets. However, EEG is largely known to have high amounts of confounding artifacts that resemble abnormal signatures of seizure, leading to iterative variability in the dataset. In really noisy time points, the labels could be entirely long, leading to over-segmented seizures. Now, the deep models that are trained to detect seizures using these noisy labels end up being highly prone to learning wrong characteristics and several false positives during testing phase. Despite this, several deep networks have emerged in the last decade to detect seizures, which are trained using general cross-entropy laws under the assumption that the clinician-provided labels PG are correct. This way, they only capture the relationship between EEG-X and the noisy label Y-hat, parameters by PG. In contrast, we propose this graphical model that captures the three-way relationship of clean label or underlying true seizure characteristics given by Y, influencing both X and Y hat. We define the posterior on Y as follows. Essentially, Y follows PG when the uncertainty Z is low, and when the Z is high, it follows its self-supervision and falls back into its own intuition. Upon marginalizing the joint distribution of Y and Y hat, we arrive at our Bayesian uncertainty-aware deep learning framework that uses the parameter PYC computed from marginalization to supervise the model. However, once we have this derived, the next challenge is to compute ZX, the uncertainty. Without any uncertainty computation, the model F theta and the whole framework would only have this top branch, where the model predicts F theta and follows the noisy label PG. However, to overcome that, we propose to use Monte Carlo dropout to compute data uncertainty in each training step. We do this by making multiple forward passes to the model with random dropout to get empirical samples of the posterior. We take the average of these samples to obtain the self-supervision and compute the entropy to get the uncertainty, and from here the marginalization gives us PYC. Once the optimal point is obtained using training with this lower branch, we no longer need it, and the model only the top branch can be used to get the F theta from model, which estimates PYC, the clean label. We use this strategy to train and test on two datasets, an in-house simulated EEG dataset using Moodasarige framework and the publicly available Temple University Hospital corpus, both containing 120 subjects and multiple seizure recordings. We used 10-fold cross-validation setup that is repeated 5 times for our evaluation. Since BUNDL is model agnostic and it can be used to train any deep network, and here we compare with 3 state-of-art neural architectures given here. In comparison with the cross-entropy laws, which has no noise assumption, a model sees a steady improvement. In simulated datasets, all metrics are better using BUNDL in all 3 models. On the TUH dataset, FPR and latency significantly improve with comparable sensitivity. Further, we compare against 2 baseline methods, self-adaptive training, which is an algorithm that uniformly changes the supervision of all samples, and noise adaptation layer, NAL, which adds additional layers on top of the existing architecture to predict noisy and clean labels. On simulated data, all metrics improve with BUNDL. NAL performs similarly but has high FPR. There is no significant difference between self-adapt and CEL, suggesting that it's not exactly learning any clean label signatures. Similar trend is seen on TUH data with deep SOZ. Here, there's a small decrease in sensitivity, and NAL has better sensitivity at the cost of very high false positive rate. Further, this drop in sensitivity could also be attributed because we're comparing against the noisy labels provided by the clinicians in the TUH dataset. However, the reduced false positive rate aids in the downstream task of onset zone localization. By reducing the false positives in detection, it also reduces the false onset zone localization on the downstream task and rightly predicts the onset to right frontotemporal in this patient and several others as seen in the downstream task. In conclusion, here we have proposed BUNDL, a robust training framework to train with noisy labels, which is model agnostic and hence can be used to train any deep network with no parameter overhead. It shows improved performance on multiple datasets and downstream tasks, showing its robustness. We have shown that it can handle the complexity of medical applications and particularly EEG and overcomes inter-rater variability. Further, we note that it can be easily adapted to other modalities and our future work would involve applications and multi-class problems beyond EEG. Thank you.